The rules for mapping unary relationships. In a unary relationship, you have two situations. One is a one-to-many relationship, the other is a many-to-many relationship. If you see a one-to-many relationship, what do? Well, think about this. You have a unary relationship, and that means there is only one entity type here, right? And it has a one-to-many relationships. Well, if you see only one entity type, then how many tables do you have? Well, just the one table. And it's a one-to-many relationship, so you don't create a table for that. And the only rule that comes with the one-to-many relationship is that the primary key of the one side becomes the foreign key of the many side. However, here you only have one table. So that means that the primary key of this table becomes the foreign key of the same table. So how does this work? Well, let's take a look at an example here. Employee is managed by another employee. That's a one-to-many unary relationship. You see one entity, you create one table. And employee ID is the primary key. So you also need to make employee ID the foreign key of the same table, right? Because of the one-to-many relationship. So what you do is you put employee ID here, but you call it a different name. You call it a manager ID, because the relationship is employee manages other employees. So it still is the same rule. You see one entity, you create one table. You see a one-to-many relationship, you make sure the primary key of the one side becomes the foreign key on the many side. What if it's a many-to-many unary relationship? You have a unary relationship with a many-to-many relationships. What you do is, well, you see one entity, you create one table. And you see a many-to-many relationship, you create another table. So two tables, one for an associative relation in which the primary key has two attributes, both taken from the primary key of the entity. So what does this mean? If you look at this example here, this is the bill of material situation. You have an item that contains other items, and one item can be part of many other items. So it's a many-to-many unary relationship. So what you do is, for the first entity item, you create a table. And then you create another table for the many-to-many relationship, kind of like an associative entity here. The other rule about many-to-many relationship is that the primary keys of the entities will become the primary keys of the associative entity. Here, since we only have one table and the primary key is item number, well, then this needs to appear twice in the associative entity. But so we cannot name them the same because it will violate the requirement for the relation, right? So we have to name them differently. One is called an item number. The other is called a component number. So the component number essentially is an item number. We just call it a component number to differentiate from the item number. How do we map the ternary relationship? For the ternary relationship, again, one relation for each entity and one for the associative entity. So you will have four tables. And the associative entity has foreign keys to each entity in the relationship. Let's take a look at this example. This example shows the ternary relationship among physician, patient, and the treatment. There is an associative entity here called the patient treatment that links all these entity types together. You create four tables here. One for patient, one for physician, one for treatment, and then one for the associative entity here. The associative entity here is going to take the primary keys of the other three tables as the foreign keys: patient ID, physician ID, and treatment code. However, if you use the combination of these three as the primary key, they probably would not be unique enough because the same physician may use the same treatment on the same patient multiple times. In order to make it unique enough, we're going to also include the treatment date and the treatment time as part of the primary key. The rules for dealing with supertypes and subtypes. One relation for supertype and for each subtype. So if you see one supertype and two subtypes, then you have three tables. And then the supertype attributes go into supertype relation, and the subtype attributes will go into each subtype. And the primary key of the supertype relation also becomes the primary key of the subtype relation. So the supertype and subtypes will have the same primary key. And you will also establish a one-to-one relationship between the supertype and each subtype. Let's take a look at an example here. In this example, we have a supertype employee and 3 subtypes, like hourly employees, salaried employees, and consultants. As the rule said, for each entity type here, we are going to create a table. So we are going to create 4 tables here. As you can see, we have 1 table for employee, the supertype. We have 1 table for hourly employee, 1 table for consultant, and 1 table for salaried employee. Then the primary keys of the subtypes will be the same as the supertype. So we are going to use employee number as the primary keys for all the subtype tables. However, in order to differentiate them, we are going to name them differently. For the consultant, we are going to call it C employee number. For the salaried employees, we'll call it S employee number. And the hourly employees, we are going to call it H employee number. But they're essentially the same thing as employee number. They are just named differently. All right, so these are all the rules for transforming ER diagrams into relations. Did you remember all of them? The next topic here is normalization. That's the second activity you're going to perform in logical database design. Data normalization is a tool to validate and improve the logical design so that it satisfies certain constraints that avoid unnecessary duplication of data. It's the process you go through to decompose a large table into multiple smaller tables, so that all these smaller tables are well-structured relations. Sometimes when you get a large table, there will be lots of data duplications and they are not processable. So that's why you go through the normalization process. Well, actually, in an ideal world, if you start from scratch to develop a database and you go through the process carefully and did everything right, then in most cases you don't actually have to do normalization. But in the real world, what happens is you may get some information from an application and it's just a one string of data, and you have to somehow break it down into small pieces and put it into different tables to make it more normalized. Or sometimes you may start with a paper-based system. All you get is just some forms people used to use to record data, and then in order to transform these forms into tables, you have to break these fields on the form into smaller chunks and put it into different tables. So that's the process of normalization. It's a very important process because it will allow you to create tables that are well structured without anomalies. So what is a well-structured table? A well-structured table is a relation that contains minimal data redundancy. So if you look at the tables we created in the last example, there is very little data duplication. The only data duplication you will see is the primary keys and the foreign keys, because the same primary key will become the foreign key in another table. So that's the only data duplication you will see. And that's the only data duplication you should see in the table if they are well structured. A well-structured relation also allows users to insert, delete, and update rows without causing any data inconsistencies. There are 3 different types of anomalies that may occur if you have a table that's not normalized. One is called assertion anomaly. That means there will be inconsistency in data when you insert data into the table. And the other is called deletion anomaly. That's inconsistency happens when you delete something from the table. And also modification anomaly. That's when inconsistency happens when you update the data in the table. Let's take a look at an example here. So for example, in this particular example, we have an employee table. In this employee table, we have a number of fields. We have employee ID, name, department name, salary of the employee, the course title of the course that employee took, and the date on which the employee completed the course. So we have all this information in the same table. The first question I want to ask you here is, which one is the primary key for this table? employee ID. If you look at this table, is it unique? It's not unique. The same employee ID appears in multiple places. Course title, well, you also have duplicates in course titles, and also you have no value here. It's a combination of employee ID and the course title, right? So that's the primary key for this table here. However, this table has a number of problems. It's going to cause some anomalies when you try to insert the data into it, when you try to delete data from it, and also when you try to update the data in the table. For example, let's say if we try to insert a new record into this table. Let's say we hired a new employee, John Smith, and this is the first day of John Smith at the job, and John Smith hasn't got a chance to take a course yet. So we put in John Smith's employee ID. John Smith works for the accounting department, salary. Well, hasn't taken a course yet, so we're going to leave the course title empty, the date complete empty. Okay, well that creates a problem. DBMS is going to send you an error message. Why? Because you cannot have no value for the primary key, and the course title happens to be part of the primary key for this table, right? So that's the first anomaly you are going to run into, and that's called insertion anomaly. Let's say if we want to delete a record from this table. Let's say we want to delete the record of Alan Beaton, employee number 140. Alan Beaton no longer works for us, so we're going to delete Alan Beaton's information from this table. Well, as we delete this record, what happens is not only have we deleted the Alan Beaton's information, we also have deleted the information that there is a course called the tax accounting that was given on December 8th, 2000X. Do you see that? So we are deleting more information than we intend to. So that's called a deletion anomaly. What if we try to update information in this table? Let's say we are going to give Susan a raise. So we are going to change the salary to $50,000. So we make the change here, and then we see, well, Susan's salary information appears in multiple places in the table. So we actually have to go to multiple records and change the salary information here. Do you see that? And if we forget to change one of the salary information, then there is inconsistency in the data. So that's called update anomaly. So the reason why there are these three types of anomalies is because this table is too big. It contains information about multiple entities. It's got information about employee. It's got information about the course the employee takes. That's why the table has all these anomalies. So in this case, we need to go through the data normalization process to decompose this table into smaller and well-structured tables to get rid of these anomalies. This slide shows you the anomalies that I just mentioned in the previous table. Before we can talk about the data normalization process, there are a number of concepts you need to understand. The first concept here is called functional dependency. That means the value of one attribute determines the value of another attribute. For example, if you have a table, employee table, and you have employee ID, last name, first name, address, and department ID. ID here is the primary key. Using the concept of functional dependency, we can say that the employee ID determines the last name, determines the first name, determines the address, and determines the department ID. The reason is that the value for last name, first name, address, and department ID depends on the value of the ID of the employee. So if we know the employee ID, we can figure out the employee's last name, first name, address, and the department the employee works for. So that's the concept of functional dependency. So usually the primary key will functionally determine the other non-key attributes. And the other concept here is the concept of a candidate key. A candidate key is a unique identifier. However, it may not be a primary key. It's a candidate for primary key. What is a candidate key? Well, if you use a combination of last name and first name and address, well, maybe that's unique enough. However, it doesn't mean that these three together should be the primary key, because ID is a much better primary key. But these three together is a candidate key because it's unique enough, so it's a candidate for primary key. This picture shows you the different normal forms you're going to see. We only look at the left side of this picture. We usually normalize the table until it reaches the third normal form, because fourth normal form or the fifth normal form are very rare. It almost never happens. So we usually only go to the third normal form and stop. You start with a table with multi-valued attributes. You remove the multi-valued attributes, and then all the values in the table are atomic. Now your table is in the first normal form. Remember the first slide of this lecture, it says that all relations are already in the first normal form, because in all relations the values are all atomic. So all relations are already in the first normal form. To move a relation in the first normal form to the second normal form, you need to remove what's called a partial dependency. Okay. So what is a partial dependency? Well, let's say you have four fields, A, B, C, and D. And in this table, A and B together is the primary key. If these are the primary key, then it means that A and B together can determine C and can determine D, because the primary key is supposed to determine the values of other non-key attributes. What if at the same time B can also determine the value of C? Then this is called a partial dependency, because part of the primary key can determine another non-key attribute. When you remove the partial dependency from the second normal form table, what you do is you break this into two tables. You're going to have A, B, the primary key, and a D, because A and B together can determine D. And then you create another table with B and C, because B can determine C. You break this table into two tables to remove the partial dependency. So now these tables are in the second normal form. To move a table in the second normal form to the third normal form, it will require you to remove the transitive dependency. What is transitive dependency? Transitive dependency looks like this. Let's say you have A, B, and C. And A is the primary key. If A is primary key, then A can determine B and it can determine C. But what if at the same time B can also determine C? Right? So B is a non-key attribute, but the non-key attribute can determine another non-key attribute. So that's called a transitive dependency. So in this case, what you're going to do is you're going to decompose this table into two tables. A determines C and then B determines C. So now this table is in the third normal form. Okay, so you first get rid of the partial dependency, and then you get rid of the transitive dependency. It doesn't mean that all the tables will have both partial dependencies and transitive dependency. Sometimes the table only has transitive dependency. So that means the table is already in the second normal form to start with. Right? So all you need to do is just get rid of transitive dependency. But sometimes the table only has partial dependency. And that means once you get rid of the partial dependency, it's in the third normal form. So our goal is to transform the tables into the third normal form tables. So let's look at some examples here. The definition for the first normal form is that there is no multi-valued attribute. Right? Every attribute value is atomic. So for example, this table has multi-valued attribute because if you look at product description here, we have multiple values. So it's not in the first normal form. Now the table is in the first normal form because every cell here is atomic, only has one value. But the problem with this is there are lots of data duplication. As you can see here, the customer name, value furniture, the customer ID, the address, there are lots of duplications here. So obviously this table is not well structured. It will have the insertion, deletion, and update anomalies. How do we move this to the second normal form? We want to make sure that we get rid of the partial functional dependency. That means every non-key attribute must be defined by the entire key, not by only part of the primary key. It's the same table that we just looked at, except without the data here. Right now, the primary key is the combination of order ID and the product ID. Well, order ID will functionally determine order date, customer ID, customer name, and customer address. Right? And the product ID can determine product description, product finish, and the unit price. And the product ID and order ID together can determine the order quantity. We are seeing partial dependency here because the product ID is part of the primary key and it can determine other non-key attributes. And the order ID is also part of the primary key and it can determine other non-key attributes. To get rid of the partial dependency, we are going to decompose this table into 3 tables. We are going to create an order line table, which has the order ID, product ID determines quantity, and then we also have a product table and a customer order table. Now the first 2 tables are in the third normal form. What about this table? Well, if you look at this table, it has order ID as the primary key, right? But the customer ID here can also determine the customer name and can determine the customer address. Well, and the customer ID here is a non-key attribute. So what we have here is a transitive dependency. In order to get to the third normal form, we need to get rid of the transitive dependency. The definition for the third normal form is that the table has to first meet all the requirements for the second normal form plus no transitive dependency. We will again decompose the table into 2 tables. Now we have one table called order, the other table called the customer. All the non-key attributes are determined by the primary key, right? So there is no transitive dependency anymore. In normalization, what we did was we are breaking one large table into smaller tables. And sometimes you may run into a situation where you have multiple developers developing different parts of the database. And then eventually you need to merge these designs together into one design of the database. One designer has a table called customer, and another designer also has a table called customer. When you need to put these 2 tables together, you are merging these relations. The first situation in which you need to merge the relation is called the view integration. When you create different views for different users, when you put them together, you probably need to merge some of these views into relations. A number of issues you need to look out for when you merge relations. The first one is synonym. You may have 2 or more attributes with different names but same meaning. Because different database designers may call the same attribute differently. When you put them together, you cannot treat them as 2 different attributes. You need to treat them as the same attribute. For example, one designer may call it student ID, and the other designer call it student number, but they are essentially the same thing. You want to make sure that you recognize these synonyms and treat them as just one attribute. The other situation is that you may have attributes with the same name, but actually different meaning. So you may see those fields are called address, but one actually is referring to the mailing address, the other is referring to the permanent address. So you need to recognize that and treat them as 2 separate attributes. And then there is also transitive dependency issue here. This is rare, but it can happen. Sometimes you have relations that are already in the third normal form before you merge them together. But after you merge them together, it has transitive dependency. For example, let's say you have student ID and also student major. You have another table with student ID and advisor. You see these 2 tables and you say, well, maybe these 2 tables can be merged together. They're both about students, so you can merge these 2 tables together. So what you do is you merge these 2 tables together, so now you have student ID as the primary key and then major and the advisor. It makes sense, right? What if in this particular university there is only one advisor for every major? Well, but there is a transitive dependency, right? If you know the major, you know who the advisor is. Your table is not in the third normal form anymore, even though these 2 tables were in the third normal form. After you merge them, there is a transitive dependency here. So what do? Well, you have to break the table into 2 tables. So you have student ID and major, and then major advisor. So it's basically just a reshuffling of the fields here. So now these 2 tables are in the third normal form. Another thing you want to watch out for is the supertype and subtype relationships. They may be hidden prior to merging. For example, if you have a table that's car and another table that's truck. You may have a supertype, subtype situation, vehicle with two types of vehicles. So that's another thing you want to pay attention to when you merge relations together.